Imagine this. You find yourself on the surface of the moon. The desolate yet strangely beautiful lunar landscape stretches out before you. The Earth hangs in the sky, a distant blue marble. You take a step, lose your footing, and begin to fall. What happens next? This isn't Earth. Gravity doesn't have the same grip here. There's no atmosphere to speak of, no air to resist your descent. Would you plummet rapidly towards the surface or float gently down? The answer, as with most things in science, is nuanced and fascinating. Over the next few minutes we'll journey together to understand the physics of a lunar fall, exploring the surprising ways our familiar experience of gravity changes in this alien environment. Fasten your seatbelts, space cadets, it's going to be an enlightening ride. The moon, our celestial companion, isn't just smaller than the Earth, it's significantly less massive. This difference in mass translates to a weaker gravitational force. In simpler terms, the moon's gravity is about 1/6 that of Earth's. What does this mean for our lunar tumble? It means you'd fall slower, much slower. On Earth, objects accelerate downwards at 9.8 meters per second squared. On the moon, that number plummets to a leisurely 1.6 meters per second squared. This weaker gravitational pull has some interesting consequences. Remember the graceful slow-motion leaps of the Apollo astronauts? That's lunar gravity at work. While you wouldn't be able to leap tall buildings in a single bound, a gentle hop would send you soaring far higher and for a longer time than here on Earth. Here on Earth, we take our atmosphere for granted. We breathe it, we curse it when it whips up a storm, sending heavy winds to rattle our homes and storm clouds to darken our skies. But we rarely consider its impact on our everyday physics. From the way leaves gently fall to the ground to the way objects slow down as they move through the air, the moon, however, has no such luxury. Its barren landscape is a stark contrast to our vibrant Earth. It's a vacuum out there, devoid of the comforting blanket of air we're used to. The starry sky above the moon is unfiltered by any atmosphere, making it appear darker and more foreboding. This lack of atmosphere has a profound effect on our hypothetical fall. Without air, there's no medium to slow us down. No air means no air resistance. This was famously demonstrated by astronaut David Scott during the Apollo 15 mission, when he dropped a feather and a hammer simultaneously, and they hit the ground at the same time. On Earth, air resistance puts the brakes on falling objects, limiting their terminal velocity. Parachutists rely on this resistance to slow their descent and ensure a safe landing. On the moon, there's nothing to slow you down. The absence of air resistance means that objects and even astronauts fall unimpeded. This means that, while your initial acceleration would be slower due to lower gravity, you'd continue to pick up speed for longer. The moon's gravity is only about 1/6 of Earth's, so the sensation of falling is different. By the time you hit the ground, you could be traveling at a surprisingly brisk pace, even if it doesn't feel as dramatic as a fall from the same height on Earth. The impact, however, can still be significant. The moon's lack of atmosphere and lower gravity create a unique environment where the rules of physics play out in fascinating ways, reminding us of the delicate balance that makes life on Earth so extraordinary. So, we've established that you'd fall slower on the moon, but accelerate for longer. This is due to the moon's gravity being only about 1/6 as strong as Earth's. As a result, the pull you feel is much weaker, causing you to descend more gradually. However, because there's no atmosphere to create air resistance, you continue to pick up speed until you hit the ground. What does this mean for your impact velocity, the speed at which you hit the ground? Essentially, it means that while you fall more slowly, you still gain speed over time, just at a different rate compared to Earth. This is where things get really interesting. The dynamics of falling on the moon are quite different from what we're used to here on Earth. Let's say you fall for 5 seconds on the moon. During this time you would continue to accelerate due to the constant pull of lunar gravity. Without air resistance, you'd reach a velocity of about 8 meters per second, which is quite significant when you think about it, roughly 18 miles per hour. This might sound fast, and indeed it is, especially when you consider the lack of atmospheric drag to slow you down. But consider this. A fall from just 3 meters about 10 feet on Earth can result in a similar impact velocity. This comparison helps put things into perspective. On Earth can result in a similar impact velocity. The key difference is the environment in which the fall occurs. This isn't to say a lunar fall would be harmless. The impact would still be quite forceful. You'd still hit the ground with considerable force, enough to potentially cause injury if you're not careful. And the lack of air to cushion your impact wouldn't be pleasant. The absence of an atmosphere means there's nothing to slow you down before you make contact with the lunar surface. However, the reduced gravity significantly decreases the risk of severe injury from a fall of the same height compared to Earth. This is because the weaker gravitational pull means less force is exerted on your body upon impact, making lunar falls somewhat more forgiving. We've talked about gravity and the lack of atmosphere, but what about the surface you'd be landing on? The moon's surface is covered in a layer of fine, powdery material called regolith. This regolith, a product of billions of years of meteorite impacts, adds another layer of complexity to our lunar fall. Regolith is incredibly fine, almost like flour. It's also surprisingly deep in places, potentially cushioning your impact. Imagine falling into a giant pile of dust. Not the most pleasant experience, but certainly softer than slamming into solid rock. However, regolith is also loosely packed. This means it wouldn't provide the same level of support as, say, a pile of sand. You'd likely sink into the regolith upon impact, potentially kicking up a large cloud of dust in the process. Let's take a step back and compare a 5-second fall on the moon to a similar fall on Earth. The differences are quite fascinating and highlight the unique characteristics of each environment. On Earth, a 5-second fall would cover a much greater distance due to the higher gravity. Earth's gravity is about 6 times stronger than the moon's, pulling objects down with much more force. You'd reach a much higher velocity, accelerating rapidly as you fall. This is why skydivers can reach speeds of up to 120 miles per hour during freefall. And the impact would be significantly more forceful. The energy upon hitting the ground would be much higher, making falls on Earth potentially more dangerous. The presence of air resistance on Earth would also play a role. As you fall, the air molecules create drag, which opposes your motion. Your body would encounter drag, which increases with speed, eventually balancing out the force of gravity, slowing you down and limiting your terminal velocity. This is why skydivers deploy parachutes to slow their descent and ensure a safe landing. This, combined with the cushioning effect of the atmosphere, helps to reduce the severity of the impact. The air acts as a buffer, absorbing some of the energy from the fall, would make the impact less severe than a similar fall on the moon, where there is no atmosphere to provide such cushioning. Even though you'd be traveling at a higher speed, the lack of air resistance on the moon means there's nothing to slow you down as you fall. In essence, falling on the moon is a balancing act between lower gravity and the lack of atmosphere. You'd fall slower, but accelerate for longer, covering less distance in the same amount of time, and there'd be no air to cushion your impact. This makes falls on the moon unique and potentially more dangerous in their own way, despite the lower gravity. Of course, our exploration wouldn't be complete without considering the diverse landscape of the moon. Imagine falling into a deep lunar crater, the towering walls rising around you, or picture tumbling down the slopes of a lunar mountain range, the jagged peaks a stark reminder of the moon's violent past. Each of these scenarios would present a unique set of challenges and outcomes. The slope of the terrain, the presence of large rocks or boulders, and the depth of the regolith would all influence the severity of your fall. The moon, while seemingly barren, is a place of incredible variety. Our understanding of lunar falls must account for this diversity, recognizing that each tumble would be a unique story etched onto the dusty canvas of the moon's surface. Close your eyes for a moment and imagine the scene. You're standing on the moon, the Earth a distant jewel in the sky. You lose your footing and begin to fall in slow motion, the lunar landscape scrolling beneath you. There's no rush of wind, no feeling of your stomach leaping into your throat, just the strange sensation of silence and weightlessness. You hit the ground, sinking into the soft regolith. A cloud of dust billows around you, slowly settling as you pick yourself up, brushing the lunar dust from your suit. You're a little shaken, but otherwise unharmed. This is the reality of a fall on the moon. A slower, gentler, yet strangely surreal experience. It's a testament to the power of physics and the unique environment of our celestial neighbor.